Okay, welcome. Next session is going to be about load balancing VMs in Kubernetes. I have one small request. When there will be questions, please do not leave the room because you will disturb the speakers. So if you can stay, there's enough time actually to leave the room after the session. So Yanir, stage is yours.
Thank you very much. So hi guys, my name is Yanir Quinn. I've been working in Red Hat for the last 2 interesting years. I'm a part of the overt SLA team, the Red Hat virtualization. And currently I'm mostly working around Cuberoot. So let's start. Basically, the topic today is the need for load balancing in Kubernetes. And to talk about it, we need to first go over what is Kubernetes in a nutshell and also what is Cuberoot, how scheduling works in Kubernetes, and then understand why do we even need load balancing. After understanding the need, we'll see some of the projects already out there and concepts in Kubernetes, and also we will focus on one major project in Kubernetes incubator called the scheduler for load balancing. After that, we'll see what else might be done around that area with an emphasis on scheduling simulation. And finally, all of that will come down to load balancing virtual machines in our Kuberoot fold with a load balancing experimental algorithm. We'll have an example at the end. So first of all, Kubernetes. So Kubernetes is, as you know, most of you might know, is an open source platform designed to auto-scale deployment, automate deployment, scaling, and orchestrate the containerized applications, doing all that on a cluster level. So at the minimum, Kubernetes can schedule and run containerized application across multiple virtual or physical hosts, and they could be around up to 5,000 of them, doing that in a manner that maximizes the host's resources. And Kubernetes containerized infrastructure allows you to control and automate application deployments. In addition, it also allows you to mount and add storage to keep these applications in a stateful state. Meaning, because containers usually have unfurled disk files that will be lost after they're gone, we need to have persistent volumes to keep stateful data and also allow containers to share data among themselves. So it should be easy to scale containers application and resources on the fly. And Kubernetes is also a declarative platform, meaning I'm telling Kubernetes using a specification file usually. Usually these are YAML files. How do I want applications to run? And it's guaranteed that the applications will run that way. It also provides monitoring and health tools for health checking and self-healing, etc. To understand a bit about scheduling and how scheduling works, I'll talk about some of the components in Kubernetes. I won't go over the entire architecture. So basically, Kubernetes runs on top of an operating system, and it interacts with pods running on nodes. Nodes, for that matter, are our hosts. So let's zoom a bit to Kubernetes node and what it contains. So our scheduling unit in Kubernetes is a pod. A pod is a collection of containers, one or more containers that have shared storage, networking, and being a declarative language, Kubernetes is, you create a pod with a specification file. The specification file will contain image data, storage data, resources I want to allocate for a specific pod, such as CPU and memory. And these pods run on the host I mentioned, either physical or virtual. In a Kubernetes node, you have services that keeps the node running and communicate with the outer world. One of them is a kubelet, which is some sort of an agent for the node to communicate with other components in Kubernetes and keep an eye on the state of the world and the changes and other commands. Also, it might contain services such as Docker or other container runtimes and a kubeproxy. Some of the master components relevant to this lecture is, first of all, the API server. So the API server is the gateway to Kubernetes. It's basically the front end. It receives commands from the outer world, from DevOps, for example, and relays them down to Kubernetes, and this is how we communicate. Another major component is etcd. etcd is the backend store of Kubernetes. Kubernetes runs on resources. One resource, for example, is our pods. So etcd keeps in a key value pair all the information needed for our world, and it's in a stateful way. So a pod will be contained in etcd with its identity, and we can always examine its state. So one of the components in Kubernetes examining the state of the world is a scheduler. But before I talk about the scheduler is one of the background threads in Kubernetes called controllers. Each controller looks at the state of the world, meaning in etcd, and acts upon them, running in the background for a defined ratio for examining etcd. So the basic job of a scheduler is to look if a pod was created and it doesn't have a node assigned to it, takes that pod and schedule it on top of one of the nodes in Kubernetes. So we talked very briefly about Kubernetes, and now we get to Kuberoot. So Kuberoot basically comes to converge two infrastructures. We have our Kubernetes infrastructure, which is about containers, but we still want to manage VMs. So Kuberoot is an add-on for Kubernetes that allows us also to manage virtual machines alongside containers. This is a classical example. So containers is the strong buzzword around the world. It's considered the strongest way to go right now. It's faster, it's stronger, it's soaring out, it's scalable and can soar really high, like Superman, for example. On the other hand, we still have our virtual machines. So they have their old bulky utility belt with a full hardware stack starting from BIOS and network adapters, storage virtualization, CPU, and more. But the world is still not ready to get rid of virtual machines. The world still needs also Batman, for that matter. So that's the main reason for us to have a converged infrastructure. We don't want to manage two infrastructures that will give us a large overhead and duplicate resources, etc. So for that, we have Kuberoot. So Kuberoot comes on top of Kubernetes and acts with it. It drops really easy to a Kubernetes cluster. You don't need to add an additional host setup. It's really simple to install. And it takes all of the Kubernetes benefits and capabilities, such as scheduling and also managing it in a declarative way. So I talked about pods, but Kuberoot is about virtual machines. And we represent in Kuberoot virtual machines as the way pods are represented in Kubernetes, in a declarative way, and they are managed the same way a pod is managed in Kubernetes. To understand the concept of load balancing in Kubernetes and virtual machines, think about it this way. A virtual machine is running on top of one or more pods. So when I'll talk about scheduling pods, it's basically scheduling virtual machines with a twist. So just a quick, simple overview how scheduling works in Kubernetes. So you have the client side where you can run commands using kubectl. With kubectl, you can initiate a command given the specification file as Kubernetes being a declarative platform about the pod. That file will contain, as I said, the images, the image storage, and also for scheduling matters, how much resources I want it to consume or what is the maximum it can consume or minimum it needs. So we created a pod, and now we have a pod definition. The pod is not running on any host yet. Once we created a pod, its data is stored in etcd, but without any host. So the scheduler, being a controller that looks at the state of the world, notices, hey, I have a pod right now. It doesn't have any host. So I'll assign that pod to node X. The scheduler works according to scheduling policies and some threshold you want to define. Examples from our overt world can be power saving, evenly distributed, and it acts with filters, or in Kubernetes world are predicates, and also weights or priorities in Kubernetes world. So doing all of these calculations, it finally comes out with a best host for that specific pod. Once it decides what's the target host or the target node, it updates the state in etcd. So the pod is now with a state that it's assigned to specific node X for that matter. The agent running on node X notices that something has changed in etcd. The pod is now assigned for node X in etcd, so it said, hey, I'm supposed to run that pod, and finally starts a process which it runs the pod with all of its container on top of it. So that's a very simple flow of scheduling in Kubernetes. So now we talked about scheduling, let's talk a bit about load balancing. So here's a blast from the past, or this defragmenter. So it will help us a bit to understand why do we even need load balancing. So like your classical old hard disk, when you create files, delete files, add capacity to it, you create holes. And the state of the hard disk is not as good as it was at the start. And this defragmenter, for that matter, does the defragmentation work and gets your disk to be in a more consistent state. Same thing goes to Kubernetes cluster. You can look at pods as files. Pod creation, pod termination, adding more nodes will get the cluster to be in an, I won't say unstable, but not in an optimized state. So one of the main reasons for that scheduling decisions in Kubernetes are made only once. Once you create a pod, and once it's assigned to a node, it won't be moved again. The decision is final until the pod is terminated, and then a replacement one will come, and the scheduler will just schedule it to a new node. But again, pods are killed, and then they don't live anymore, and a replacement pod comes instead of them. So, because of that, we need a way to optimize the cluster layout. We want to look at the situation and decide, okay, I have some pods running on certain nodes, and maybe if shifting them to other nodes will optimize the cluster layout and give me a more evenly distributed cluster. Or maybe I can switch some pods to other nodes and save some power by disabling one node. A complete framework of that doesn't exist yet in Kubernetes, but there's work being done and work that has been done for now. So in the Kubernetes world, let's take a look about a few of the examples that currently exist in Kubernetes. So we have the classical scaling, autoscaling. So it's the autoscaler. It simply notices the state of the Kubernetes cluster, and if it sees that the resources are almost exhausted, it will automatically bring up a node. Bear in mind that it brings up the node and doesn't move existing pods yet to the new node. This is for upcoming nodes, for newly created nodes in the future, so I won't worsen the state of the cluster. Another thing is eviction policy. Eviction policy, you can look at it also as a concept, but for balancing right now, you can look at it as a concept for a specific node and not for the entire system. Meaning, I have a node and I set defined thresholds for that node. Once I reach these thresholds after a grace period you defined, the node will start evicting pods from that node until it reaches a stable state again. Again, it's in the concept of one node. From other virtualization concepts and maybe other cluster concepts, you might have heard about affinity, which basically means a pod can run along other pods, or a pod can run on certain hosts, and you have also anti-affinity, which means the complete opposite. In Kubernetes, you have also the concept of taints and toleration. Taint means that a node will repel certain pods according to defined labels and definitions, but you can put on a pod certain toleration that means, okay, the node will reject this and that pod, but if I have a toleration, then a pod can be scheduled on that node. An example for load balancing world, or maybe for damage control, one taint can be once I reach out of space or out of memory in a certain node, then it applies immediately an eviction for the pods running on a node, because it cannot tolerate out of disk. And finally, another solution in Kubernetes is about pod priority and preemption. Basically, it's scoring your pods, meaning I want to grade the pods from 1 to 1,000, for example, being 1,000 the highest rank. So critical pods will get 1,000, and not so critical pods will get something in the middle or maybe less. And once I reach a specific threshold, critical pods that will have a high score are favored over pods that have a lower score. So for that matter, I want to create a new pod which is critical. Or I have a critical pod that went down and was created again and I need it to run. So pods with low priority will be preempted, they will be moved, and the preemption will cause critical pods to be scheduled on a node. These are partial solutions for the system that does relieve the state of the system, but it's still not a complete load balancing solution. So this was Kubernetes, and also Kubernetes has a great repository called Kubernetes Incubator with interesting projects in it. And two of the projects related to load balancing are cluster capacity and the scheduler. So before I talk about the scheduler, just a quick overview about cluster capacity. Cluster capacity means I get a pod specification with its, for that matter, desired resources, and it takes a snapshot of the state of the cluster and then tries to see on how many nodes the pod will be deployed on or assigned to until it reaches a certain limit, and then it will say, okay, I scheduled a number of pods and I cannot schedule any more pods. Downside of it, that it's for a specification of a specific pod, and again, not a complete solution. So we're coming now to this scheduler. This scheduler currently looks like something that is more close to a complete load balancing solution. So, like classical load balancers for workloads, the scheduler, you set a certain strategy or policy. It can be high utilization, low utilization, power saving, maybe in the future. Having set that policy, it looks for a trigger, for a state that it can enable load balancing in the system. Meaning, I got to a certain state, and now I can see that I can take down one pod, kill it, and let the scheduler reschedule it again. So once it gets to that situation, it kills the pod, evicts the pod. A pod being a part of Kubernetes concept, part of deployment or replication set or replication control will be recreated instead of the killed pod, and the scheduler, with the new state of the system, of the cluster, will probably schedule it on a new, better node than it was before. Doing all of that with an emphasis of minimal disturbance to the cluster. I don't want to start killing pods all over and evicting them over and over again, because they might not be reassigned, or it might not improve the state of the cluster. So one existing policy, for example, it's low utilization. You can see them on top. Once I see that a node has a state with a lower number of nodes than something I defined, and a low memory and CPU, it means I might want to evict some pods into that node, so I can level the system. This can be caused, for example, if an autoscaler brought up a node and it doesn't have a lot of pods running on it, and I want to balance the system. So it basically will kill a pod, and hopefully the scheduler will reschedule that pod on top of the new idle node. So again, because we're repeating that Kubernetes is declarative, and the scheduler also gets a declarative file with that specific policy. So for the example of low utilization, I'll zoom in a bit. We define specific threshold for low utilizations. So you can see at the top example that I defined, I want 20% of CPU and maybe 20 for memory is not the best example, but a simple threshold of memory that wasn't reached, and also number of pods. If a node applies to all of these thresholds and it's under it, then it triggers the descheduler to start searching for other nodes where it can evict pods from. So we can also define target thresholds for nodes you want to evict pods from. So it will be the other example. All the values above 50 CPU, 50 memory, 50 pods will cause a pod to be evicted from that specific node. So you can't just start evicting pods from every node. You can't evict critical pods, pods that are not expected to terminate, have local storage for that example. Again, they need to be a part of a deployment or a application set, so they will be recreated. Otherwise, killing them won't mean anything. And we want to evict, of course, best effort pods before critical or burstable pods. So something is still missing here that might contribute also to the descheduler project. We want to know, before we evict a pod and let Kubernetes create a new one, if a new pod will even be scheduled on some node. Maybe we do all of this work in vain. We want to have a more accurate simulation of the system state and reassignment. Not only taking a snapshot, but maybe doing it in real time. And finally, actual replacement of pods to better nodes. So, for that matter, we want to have the ability of scheduling simulation. Scheduling simulation, or dry run functionality for that matter, doesn't exist yet in Kubernetes. It's an open issue. We are also working to contribute on that matter to have the ability for dry run scheduling. So scheduling simulation basically means you take a dry run endpoint that will take a pod, and eventually will tell you where the pod will be created, or where the pod will be binded to. Or even before, I want to see if it can be even binded to a specific node, even before getting the results. So these are two of the outputs. Very simple for a dry run functionality. So as I said, use cases can be very good for rescheduling and load balancing if I can pre-know where I would schedule that pod on a specific node. That will really help me before starting changing the cluster state and load balancing the system. For cluster capacity analysis, for example, instead of taking a whole snapshot, I can just run dry scheduling on each pod and then see what happens. And maybe it would be more accurate instead of having time elapsed since I took that snapshot. Also for auto-scaling in Kubernetes, if I scale up a node, I want to see what happens next, etc. You also have the capability in Kubernetes to use replacement schedulers, meaning you can create your own scheduler and have maybe stricter predicates of filters. So stricter predicates, usually logically saying, they might not allow you to assign pods to nodes as easy as in the Kubernetes stock scheduler. So we want to better know how it will happen. There are some obstacles for creating this dry-run functionality on Kubernetes. Because, first of all, we don't want to affect the state of the world. We don't want to affect etcd. So we need to leverage a caching mechanism in the Kubernetes existing scheduler, which won't be easy. And also, we don't want to just evict a pod and then run it back again because I'm changing the state of the world. So it should be something more memory-wise instead of changing etcd. So it all comes down to load balancing virtual machines. All of the concepts I mentioned before. So taking Kubernetes and Kuberoot, using dry run functionality for load balancing, maybe with the scheduler, maybe another algorithm, and migrating eventually VMs. But before we talk about just running the algorithm, migrating VMs, what does it mean? So virtual machine, let's look at it in an abstract way. Virtual machines run on pod, one or more pods. And we don't want to kill virtual machines. We don't want to evict the pod that the virtual machine runs on. Killing it will say, it doesn't really create a live migration. So for that matter, what we want to do is before killing the pod with the virtual machine is creating a replacement pod and then transferring the workload of the virtual machine to the new pod as a result of load balancing and shifting a pod to another node. So Cuberoot has a new object called migration, which defines a destination node, defines what is the VM, and the status of the state. So once a migration object is created, we schedule a new pod. It schedules a new pod. When it starts, it triggers the migration, and at the end, the VM moves to the new pod. So how can it work on Kuberoot? So as I said, we have the scheduler. The scheduler evicts the first pod it sees from a specific node, and then lets a new pod be created. Kills it, and Kubernetes, and the replacement pod will be rescheduled by Kubernetes. But we don't want to kill the pod yet. So instead of it, we will just block pod eviction or pod deletions, and virtual machine migration will be in the background. We will create the migration object, a new pod will be created, and then a virtual machine will finally move there. I also talked about scheduling simulation. So we might be able to neglect the scheduler project and do explicit load balancing based on migration objects and utilizing the dry run functionality. So this is an example for a brute force algorithm that will make use of such dry run functionality. I will go all over the pods in the cluster, taking them from all the nodes, dry run them with the scheduler, and see what is the destination node. So for each pod that I found a destination node, I want to score it, give it some sort of a scoring. I don't want to score the node itself. I will score according to the node, according to its memory consumption, according to CPU, maybe other aspects you want to add later on using priorities. So I have an overall score. For that matter, let's see that the higher score is the better migration. So I scored the migration eventually. So once I've went all over possible migrations, I'll get a list of all migration results, and then like in MapReduce, I will reduce it to the best score that I have, and according to that, I will initiate the migration. So the best migration will be for the best overall, and then we'll trigger a migration event, and the pod will be rescheduled. This could be very CPU consuming since it's brute force, but it's another example how you can utilize dry run functionality in Kubernetes without using other projects, or maybe creating your own load balancer. Okay, so we talked about Kubernetes, Kuberoot, load balancing, scheduling, dry run scheduling, but it all comes down to virtual machine and balancing virtual machines. We are leveraging Kubernetes concepts using Kuberoot. We are leveraging the scheduler. And finally, we might want and wish to add more capabilities to Kubernetes, such as dry run functionality. Kubernetes are still, on their side, are adding more concepts for optimizing cluster. And you will always see in each version a new concept. Eviction policy is a bit new. Also pod priority is new. So it's an ongoing work on that area. So there's still more to come. Still work on the virtual machines world, but it's all very interesting and exciting. And I think in the following next year you'll see more concrete results in converged infrastructure for virtual machines and containers. So that was for me, and if you have any questions, I'll be happy to answer. Yes?
It's not clear to me why you want to load balance. Is it to work around isolation problems? Because if I have, like, let's say, 2 tasks that needs each 10 gigs of RAM, I know RAM is well isolated, I have no reason to want to run the machine, right?
Again, can you repeat the question?
You don't need to work around isolation problem, that you want to balance the resource utilization across machines.
You don't want to isolate the problem. Sorry. Can you? I can't hear you.
Is it to work around isolation problem within a machine that you want to load balance the tasks across machines?
So you're asking if it's about isolation and load balance. Are you talking about throughput?
He wants to understand why you need load balancing. He thinks that it's because of isolation, but understand the problem. Probably he doesn't understand the fragmentation.
No. Okay. So if I got it correctly, you think the problem is isolation, and why do you?
I'm asking what I'm asking.
Basically, again, it's about. The load balancing concept is about the system of the cluster, the state of nodes, and resource consumption. It means that I have certain containers and pods running on a node, and the node came to a certain state where I have other nodes that can take some of the pods. Again, if you're talking about isolation, you have affinity concept for that and taste and toleration, meaning I want simple containers to run on specific node if I understand correctly. These are other concepts, meaning affinity and taste and toleration. But balancing concept is around just stabilizing the system in terms of workloads and resources.
Thank you.
Yeah.
Could you, so as far as I knew, OpenVZ had a migration called VC Migrate, and there was a demo years ago where you could play Doom on one container and have the migration directly to another container, to another machine on another container while the game was still running.
In VC?
What?
You said about VC.
OpenVZ.
No, it's not. OpenVC is not supported by Kubernetes.
Yeah, I know it's not supported, but I've read that somewhere you can migrate a container to another physical host. Might be the
It's a similar approach.
Guys, can you wait 5 minutes until the questions are over? It's a bit rude.
Yeah.
Have you tried this approach or?
Again, it's not existing in Kubernetes, but I'll be happy to discuss it with you later on about this approach. Yeah.
I suppose naively for me, I associate live migration with virtualization. And is that naive? Can the same concept still apply to containers without Kubernetes?
Again, is that a naive approach for live migration on top of Kubernetes?
So is the approach scheduler only for Kubernetes, or can it be used without Kubernetes?
Okay, so you asked if the approach of this scheduler is only for Kubernetes or not only for Kubernetes. This scheduler is a project for Kubernetes, not Kubernetes. But it can also contribute for Kubernetes, for virtual machines. We can use, as I said at the end of the presentation, we can leverage it, see where we can evict a pod, and then instead of letting it evict, again, pod is in the Kubernetes world. We're talking about virtual machines running on pods. So this scheduler evicts a pod, and then a pod is recreated, and the Kubernetes scheduler just schedules the replacement pod on a new node. That's a Kubernetes concept. So integrating Kubernetes concept is blocking pod deletion, creating a replacement pod, and by creating a migration object, which is a part of Kubernetes, and then moving the VM to a new pod.
So are there non-Kubernetes applications of this concept for traditional container workloads?
So are there non-Kubernetes applications for that concept in?
Yeah, I think that's kind of the question.
Trying to understand if you can do live migration for containers only.
Live migration? No. You cannot do live migrations for containers because the concept, again, for pods, once they're terminated, it's final. Do you have room for one more question? Yeah.
What's the difference between the virtual kubelet and Kubernetes?
What's the difference? Virtual kubelet? What's the difference between virtual kubelet and the Kubernetes?
Yeah, Kubernetes, obviously what you're talking about. Virtual kubelet is a similar project by Microsoft, and the Kata container itself, are you aware of it?
I'm less familiar with the Microsoft project. Maybe it has the same concept.
Microsoft is doing integration for Azure.
So it's an integration for Azure, Microsoft. So I'm less familiar with that, but maybe we can talk about the differences later on. Do you have time for another question? Yeah.
So on those, so you have to share resources, right? And so CPU and memory, it's one kind of resource. But you have also to share the network, maybe disk IO or a swap. And so right now, yeah, real world problems about, for instance, one noisy neighbor would consume all the network of the underlying node. But I didn't find any objects yet in Kubernetes to limit this pod consumption of the network resource. And so the question is there any plans with Kubernetes to have this kind of constraints that you could apply to a pod, and that you could also use as a scheduling help to schedule the pods and spread this network load.
So you're talking about, the question was about the load balancing network load, if I understand correctly.
For instance, or disk IO or other.
Or disk IO or other concepts other than CPU and memory on top of Kubernetes. I give an example for CPU and memory just to grasp the things. In Kubernetes, you can also apply to a pod labels. Other than labeling pods, I know in terms of throughput, Kubernetes does have a load balancing, which is not the load balancer I talked about, only about throughput. But you can also apply extra predicates. I don't know if you read about the Kubernetes scheduler itself, but you can create your own scheduler with stricter predicates and maybe add filtering of networking and other priority, for that matter, also for I/O. So the concept is plain, but you can always add on top of that.
I think the rest of the questions are fine.
More questions? Okay, so we're out of time, guys. Thank you very much.